Hello, my name is Soyeon An, and I will be presenting my Termproject 3 in the field of electrical and electronic material engineering. The presentation will follow the outlined content. First, let's understand what photolithography is. It is the process of creating semiconductor circuit on a wafer using light and the mask. Before I explain photolithography process, I will provide an overview of materials and equipment involved. The foundational component is wafer, which play a role similar to that of film. On this wafer, we apply a substance called photoresist. Photoresist comes in two types, positive and negative. When exposed to light, positive photoresist become more soluble, while negative photoresist become less soluble. The component of photoresist include resin, PAC, and solvent. PAC become active under specific wavelengths of light, affect bonding between polymer differently in positive and negative photoresist. Solvent is used to control the viscosity of the photoactive compound. Next is photolithography equipment. This is the equipment that exposes the wafer coated with photoresist to light. Various types of wavelengths are used, but as the pattern becomes more evaporate, high accuracy can be achieved with a shorter wavelengths. Therefore, photolithography equipment has developed to use short wavelengths. Lastly, there the photomask. This is a plate with the desired pattern placed between the light source and the wafer. There are two types of photomask, transmissive photomask and reflective photomask, which differ based on the type of light source used. The photolithography process involves several key steps. First, the wafer is cleaned to prepare it for receiving the circuit pattern from the mask. Second, HMDS is tightly coated on the surface to enhance between the photoresist and the wafer. Neutron gas is used in sealed, narrow space to ensure even distribute of HDMS. The photoresist is evenly applied to the wafer surface through a process called spin coating. The coating thickness varies with the RPM speed. The wafer is heated to allow solvent to evaporate from the photoresist before the photolithography process. In the photolithography process, the exposure step is crucial. During this pass, light is focused on to a specific area of the photoresist, and various methods of exposure can be employed. Contact method is direct contact between the mask and the wafer. It essentially replicates the mask pattern on the wafer. While it is the most basic method, it comes with challenges such as particle issue. Proximity methods are not in direct contact but are placed close to each other. While this eliminates some particle issue, it tends to result a large image compared to the gap in the mask pattern. Projection method pattern size to 1/4 or 1/10 of original. This is achieved by ensuring the specific gap between the wafer and the mask and using the lens to focus the light. Immersion method is a wet type method known for high resolution. However, it trade-off with depth of focus. EUV method is technique that uses mirror instead of lens. In this method, light source extreme ultraviolet light. Next, post-bake. Following the exposure step, the post-bake process is performed to flatten the surface of the photoresist. Developed process, exposed or unexposed lesions are selectively removed. The final step in the photolithography process is the hard bake. Our photolithography equipment has evolved toward using shorter wavelength of light for improved accuracy. ASML's EUV equipment is prime example of this advancement. This is the basic process of EUV equipment. The light source is extreme ultraviolet and it operates by precisely colliding a carbon dioxide laser with polyethylene droplets, generating plasma. The light emitted from this plasma is then collected by mirrors to create EUV. The reticle contains chip pattern for vapor transfer, and in EUV, multi-layer reflector employing interference are used to reflect pattern light. Multi-layer mirrors are employed to direct EUV light onto the vapor, effectively reducing the reticle pattern size by a factor of 4. Vapor design in case A, negative lasers generally exhibit higher viscosity compared to positive photoresist. This characteristic can have a significant impact on photoresist process. Negative photoresist allow for application of a thicker resist layer during the spin coating process. This thicker layer can be advantaged when the goal is to create a high structure or pattern. Case A involved creating a high aspect ratio photoresist modeling. I choose for using negative photoresist. This choice offers several advantages. It reduces the exposure to impurity, shorter operation time, resulting in cost saving. From the graph, negative photoresist, specifically SU8 2100, was applied at 1900 revolution per minute to achieve the desired 150 micrometer height. The exposure method I chose is the contact method. Although there is a particle issue, PR modeling is possible in the same size as a mask. This is a photomask I designed. After spin coating, exposure is performed using a photomask. This is a final PR modeling. For case B, the path I chose is planar path. Swelling is critical problem negative PR, so it is unsuitable for fabricating nanoscale pattern. So I will choose positive PRs, but that is also have problem with high aspect ratio. This is the process before the final photo process step. Insulator deposition is performed on the vapor and CMP work is performed and oxide deposition and exposure. This is the final photolithography step. I choose the projection method. I reduce the pattern size to 1/10. I select this method because 20 nanometer gap is too narrow. I designed the photomask to be 200 nanometer, which is 10 times larger than the original 29 nanometers. This design allows for flexibility in choosing different exposure method or different type of photoresist, taking other factor into account. Thank you for your attention. Thank you.